to record this, but okay, so we have the three resonance forms here, and then we're going to do the ad hoc hybrid structure. The hybrid structure should be the actual structure that we observe in nature for this. But if we're doing, again, if we're doing VSEPR, are we going to do the VSEPR based on the hybrid structure, or are we going to do the VSEPR based on one of these resonance forms? We're going to do VSEPR always based on resonance form. You know. Why? Because it's a lot easier, and then you know, you can figure it out anyway later on how to fix. And so for the hybrid is it a single bond? No. Is it a double bond? No, this top one I'm talking about. No. This top one is between a single bond and a double bond. So if we average a double and two singles, what do we get? So think, if we average a double and two singles, a double is 2 and two singles is 2, and so we're averaging 4. If we average 4 over 3 positions, what do we get? We get, 4/3 of a bond. And so what that means is there's always a single bond there, and then the double bond is distributed over 3 structures. Good. And so that's some fraction of the bond. What was the fraction of the bond that you got for this? I can't tell if that's a 1 1/2 bond or what, but so we'll have to label it. What is it? It's between a single and a double, but where does it lie between a single and a double? Well, anyway, if I take one bond, 2 bonds, and this is 4 bonds, and average it over 1, 2, 3 structures, average it over 3 structures, I got 4 bonds averaged over 3 structures. It's 4/3, or 1 1/3. And so this is a 1 1/3 bond. We have a name for this. This is called the bond order. The bond order. So bond order 1 is a single, bond order 2 is a double. A bond order of 1.5 is a 1 1/2 bond. 1 1/3 bond. How about this one down here on the left? So it's single, single, double. So we'll take this double and average it over 3. So that means 1/3, 1/3, 1/3. We'll divide it by 3. And so we'll take the single. The single's always there. And then we'll take the double and average it over 3. So this will be a 1 1/3 bond here. 1 1/3 bond. Is that what you guys got for this? 1 1/3? No? Same thing here. It'll be 1 1/3 bond. Okay, now let's take a look at the lone pairs on the top oxygen. 2 lone pairs, 3 lone pairs, 3 lone pairs. So we're always going to have 2 lone pairs. The third lone pair is going to be there 2/3 of the time. And so that third lone pair, I'm going to just draw dotted. That's there 2/3 of the time. So the same thing with this oxygen. The third lone pair, I'm just going to dot in this oxygen here. 2 lone pairs are always there. Third one, like that. And so what we'll do is this. To figure out the charge on the oxygen, I'll take this -1 and -2. So I have -2 divided by 3 atoms. If I have -2 charge divided by 3 atoms, then each oxygen atom will have a -2/3 charge. -2/3, -2/3, -2 divided by 3 oxygen. And so that if I sum up these, so sum of the formal charges, I have 3 at -2/3, so that's 3 times -2/3, which gives us -2. So that would be the net charge there. And so this would be the hybrid structure for carbonate. That's how we draw it. We'll get out early today since we are skipped a break, so I'll just talk about it for just a little bit longer. Okay, are we good with this one? Carbonate? All right, let's move on. The next one. Get some more practice. These are what we call equivalent. But let me talk briefly about two advanced topics. And this will just be brief. One has to do with symmetry. A lot of people like to make symmetrical structures, which is good because usually the symmetrical structure is the correct structure, but not always. So if we have something like N2O, this is a question about symmetry. N2O, I'd like to put the oxygen in the middle. Oxygen loves to bridge things. For example, in alcohols, oxygen bridges carbon and hydrogen. In water, oxygen bridges two hydrogens. So no problem with oxygen bridging two atoms. So here we could throw oxygen in the center, even though this violates something because, one of our rules is that we put what atom in the center? The most electronegative or the least electronegative? The least, but that's okay because oxygen likes to bridge. And then how many electrons do we have here? We have nitrogen with 5, we have 2 of those, and then we have oxygen with 6. 10, 16 electrons. And so we complete the octets to the terminal first. We generate that. This structure does not look good because this oxygen does not have an octet. And so what we'll do is we'll have this nitrogen sacrifice, make a double bond. Actually, we'll have both nitrogen sacrifice because if just one did it, it's still not enough. And so we'll end up with this structure in which each of the nitrogens sacrifice the lone pair to make a double bond, and now we have an octet. But how does this structure look to you? Does this structure look good? Well, it looks good from an octet standpoint, but how many bonds does oxygen usually like to make? 4? 2. And so something's going to be weird about this. What's weird about this? You tell me. I've seen oxygen make 3 bonds, no big deal. It's got a positive charge, but if oxygen makes 4 bonds, what's the charge on that oxygen? Going to be +2. This is a +2 oxygen. Wow, oxygen losing 2 electrons. That's weird because oxygen likes to gain 2, right? Lose 2. And so what we call this is, we call this a high formal charge. This is a high formal charge. High formal charge is unstable, like a +2. It's unstable. The other thing is nitrogen likes to form how many bonds? 3 bonds. In this structure, nitrogen is only forming 2. So something's got to give. And what is it? It's the charge. What's the charge on the nitrogen? -1 on each. And so maybe nitrogen wasn't so generous because in the end, it looks like each nitrogen took 1 electron from oxygen, and oxygen lost 2. Does that make sense to you? Which one's stronger at the tug of war for electrons, nitrogen or oxygen? Oxygen. So this structure looks very bad from the standpoint of formal charges, but it looks good from the standpoint of symmetry. It's very symmetrical. Now, if we put nitrogen in the center, then we end up with this. And then we complete the octets. Like that. And so now we have 16 electrons here. But when we look at this, we can form multiple bonds. Which one do you think is ready to sacrifice its electrons first, nitrogen or oxygen? Which one will sacrifice its electrons first, nitrogen or oxygen? Nitrogen. So we'll go with the double bond over here, but is that enough to complete nitrogen's octet? No. So what we're going to do is we're going to throw a double bond. Oxygen's going to have to make a sacrifice too, as nitrogen already did. Now let's take a look at the formal charges here. Everybody has an octet. Nitrous oxide is neutral. What are the formal charges here? This oxygen, 2, 4, 5, 6. It's supposed to have 6. It's 0. This nitrogen, 1, 2, 3, 4. It's supposed to have 5. That's plus. This nitrogen, 1, 2, 3, 4, 5, 6. That's minus. And so maybe that doesn't look so good. Maybe what should have happened is this. Maybe what should have happened is nitrogen should have sacrificed twice, not oxygen. And so instead of oxygen sacrificing any of its electrons to make a double bond, we'll have nitrogen sacrifice twice. If nitrogen sacrifices twice, then we'll form what's called a triple bond. And that way oxygen doesn't have to sacrifice anything. And maybe this comes out better. And so this is a case where, okay, we got to make a multiple bond to satisfy the middle nitrogen, but oxygen doesn't want to sacrifice anything. Nitrogen has to do all the sacrificing. So now do the charges come out to? The charges come out to, this nitrogen is 1, 2, 3, 4, 5, that's 0. This nitrogen, 1, 2, 3, 4, that's plus. This oxygen, 1, 2, 3, 4, 5, 6, 7, that's minus. So we still have formal charges. We can't get rid of those. In fact, in order to make an octet, we cannot get rid of the formal charges. We have to take it. And so we eliminate this structure because of the high formal charge. These two structures have lower formal charge. Out of these two structures, which one's better? And so if I step back from this, the way I look at these two structures is, what's better, to have the negative on nitrogen or to have the negative on oxygen? The negative should be on, which one's more electronegative, oxygen or nitrogen? Oxygen's more electronegative. And so we would say that this is the best structure. This is the best structure because oxygen, being the more electronegative one, should be the negatively charged versus nitrogen here. Does that make sense? And so we say that this is the best structure, but then we go, wait a minute. What exactly is the difference in electronegativity between nitrogen and oxygen? And so let's go back to chapter 12 and take a look here. We go back to chapter 12 and take a look. When I go back and take a look, oxygen is 3.4, nitrogen is there really a huge difference in electronegativity? No, there isn't a huge difference. There isn't a huge difference. This is not totally dominant. In fact, these are what we call inequivalent resonance structures. So far, all we've been looking at are equivalent resonance structures. These are inequivalent because there isn't a huge difference. Both are pretty powerful. Nitrogen and oxygen are both pretty powerful. So that's what happens here. Okay, sorry, we'll stop here. Get out. So what time were we out today? 35? Okay, so we're still 10 minutes early. But these are inequivalent, so we consider both of these. Versus, option 3 in the bicarbonate, that was ridiculous. The energy was just out there compared to these. This is much more comparable in terms of energy. And so resonance forms, in other words, do not always have to be equivalent.